Hey guys, my name is Tony. I'm a second year PhD student at McGill University, and my supervisor is Professor Audrey Morris. And in collaboration with the National Research Council of Canada, we're delighted to bring you guys and present our work in carboxylated chitosan nanocrystals as a biomass-based support for gold catalysis. So first off, I'd like to kind of give you guys a brief dive into the nanomaterials in our world. I'm sure everyone knows kind of the nanoscale, so a millionth of a millimeter. And I'd like to share with you guys kind of one of the coolest things I think in the nanoscale, which is structural color. So in this blue morpho butterfly, um, the only thing that makes it blue color is actually from the nanostructure of its wings. So from this architecture, that's where the blue comes from, and I think that's really cool how that can affect our world. And so with this, a lot of applications have come around using nanomaterials. So I've only listed four there out of possible dozens, but electronics, specifically transistors, and using nanomaterials to make those smaller and smaller. Drug delivery, optics, so using quantum dots for LED TVs, and using gold nanoparticles for biosensors have been very, very prominent in our world. And so it's very important that we kind of research and develop more nanomaterials for applications. So one of the biggest fields in this is using biomass to actually make nanomaterials and as a renewable resource that we can actually sustain. So one of them is actually coming from wood. And so within the wood cell wall, you can see that there's macrofibrils that basically line it. And within this, there's a cellulose polymer within it. And so the cellulose polymer resides in these microfibrils, and there's actually two different regions, the disordered region and the crystalline region, that's actually all jumbled up within each other. And if we use acid hydrolysis, what happens is the acid attacks the disordered regions and depolymerizes them while keeping the crystalline regions, which are more intact, um, you know, intact. So what happens is they make these crystals that are on the nanoscale, and they have a high aspect ratio. They have around 200 nanometers in length. And so from this material, there's actually been a lot of applications being discovered, as well as commercialization happening at this moment. And our lab specifically focuses on using these as a support for catalysis. So this is kind of highlighting our recent work using these for a variety of organic transformations. And what we do is we kind of put metal nanoparticles onto the cellulose nanocrystals such that we can immobilize them and use them for a longer period of time. So another biopolymer that's actually being lesser looked at than cellulose is chitin. So it's actually found within shells of crustaceans such as crab and shrimp, as well as some squid, as well as fungi. It's a very high bioavailability with a market value of over 6.6 billion. However, as we know, it's largely discarded, right? We throw out a lot of shells each year. So if you go through an acid-base bath process to get rid of all the proteins and minerals in these shells, you're left with the chitin polymer. So this is the official nomenclature of it. So you can see that on the C2 unit, we have this acid-amide functional group present. And so this is the second most abundant polymer next to cellulose. However, it is highly insoluble in aqueous media. So to actually provide more applicability, you can actually deacetylate this acetamide unit into the primary amine group. And so this is what we call chitosan, one of the derivatives of chitin. And it uses basic conditions to deacetylate. And what we're left with is a very highly soluble as well as tunable amine functionality in this chitosan polymer. So there's been a lot of work in actually getting chitin into the nanoscale. So we can see here that it exists similar to cellulose in trees, where we have the exoskeleton of crab and the chitin that's embedded in a matrix of protein fiber. It actually layers itself in this kind of bourgeon structure or twisted plywood structure, which is similar to that of a cholesteric order of liquid crystals. And so how you can extract it is similar. So you use acid hydrolysis in order to get rid of the amorphous regions of chitin, and you're left with these chitin nanowhiskers or nanocrystals with the acetamide functionalities. However, there are some unfortunate drawbacks in these steps. So for example, it uses mineral acid, HCl or sulfuric acid, as well as it requires a lot of purification steps. So usually this comes in the form of dialysis, which can take, a matter of days to purify. So in collaboration with the National Research Council of Canada, the NRC, they've been able to make these chitin nanocrystals, or CHNCs, using a mild oxidant in the form of ammonium persulfate. So you can see here, it uses the oxidant to actually cleave and depolymerize this polymer, as well as oxidize this C6 hydroxyl group into a carboxyl functional group. So it's a carboxylated chitin nanocrystal. And you can see here, similar to cellulose, it has similar size domains, around 200 nanometers in length, and a high aspect ratio. Now, what we really want to do, however, is go from chitin nanocrystals to chitosan nanocrystals. Similar to the bulk version, we want the chitosan nanocrystal with the amine functionality because it has a highly soluble aqueous media, highly soluble, as well as it has the carboxyl and amine functionality handles, which we can incorporate into a variety of applications. So with the TEM images, you can see that the length and width don't really change. The aspect ratio actually stays basically the same, basically implying that the kind of morphology doesn't change with this step. And one of the most important things from this is the use of sodium borohydride. So you can see that we actually use sodium hydroxide as the basic condition. However, sodium borohydride actually is the main thing that inhibits a phenomenon called N-peeling. So N-peeling is basically the readily increasing depolymerization step that occurs in which this polymer under basic conditions would basically fall apart. And so what sodium borohydride does is it actually reduces the alditol ends to actually inhibit this step from forming. So if we don't use sodium borohydride, what we see is these nanocrystals actually turn into these kind of amorphous balls that are higher in size, as well as not retaining that nanocrystalline shape. So from this, we actually kind of really wanted to investigate how the structure is changing while we're turning this from chitin nanocrystal to chitosan nanocrystal. So on the top here, we see our bulk chitin nanocrystal, our bulk chitin in the alpha crystalline polymorph. We can see the reflections here. And once we go into the chitin nanocrystal, you can see that the overall peaks actually remain the same. And however, once we go into chitosan, this is where we see a lot of change. So we can see that we have a highly amorphous region here. So if we actually calculate the crystallinity index in all of these, you can see that going from chitin to chitin nanocrystal doesn't really change. However, once you go into the chitosan nanocrystal, this is where a stark decrease in the crystallinity occurs. And moreover, if you look at the actual kind of peaks here, these peaks actually shift to a higher degree, a higher 2 theta angle, meaning that there's actually kind of the lattice parameters within these crystals are actually changing themselves during this deacetylation step. Further, with structural comes compositional changes as well. So from chitin to chitin nanocrystal, one of the main things that we can see from the FTIR first and foremost are the NH bend here, as well as the CO stretch here, which we can actually plot a ratio of and find the degree of acetylation. So basically how many amines there are as opposed to acetamides. Another thing we want to focus on is the carboxyl COO bond stretch here. So we can realize that after using ammonium persulfate as an oxidizing agent, of course, we see this C double O to confirm the carboxyl functional group. As well as we can see that with chitosan nanocrystal, similar to what we saw in XRD, you can see that there's a stark decrease in the number of defined peaks. So further validating that we're actually losing crystallinity while we're doing this step. So now we have a characterized chitosan nanocrystal and fully confirmed. We really want to use this now as a catalyst support. So due to the high surface area from the nanoscale nature, as well as the amine and carboxyl functionalities being used to stabilize a metal nanoparticle catalyst, we went about and used this gold precursor and hydrogen reduction to actually put gold nanoparticles onto this the nanocrystal itself. So it's a very benign procedure. And from the TEM, you can see here, we actually do confirm that we have gold nanoparticles embedded onto the chitosan nanocrystal itself with relatively small polydispersity here. So we also did some surface compositional analysis using X-ray photoelectron spectroscopy. And so from this, this actually kind of is a surprising result, because you can see here that the main oxidation of gold here is actually in gold 1 instead of gold 0, which you would normally see for gold nanoparticles, which means that most of these black dots here are actually kind of aggregates of gold 1 and not metallic gold. And so what this implies is the hydrogen reduction procedure doesn't fully reduce the gold into gold 0. And we're actually getting, instead of metallic gold nanoparticles, we're getting gold 1 aggregates into kind of nano dimensions. And so with this material, we kind of wanted to see how it can be used as a catalyst in itself. So one of the main reactions we use is the catalytic reduction of 4-nitrophenol. And we want to focus on this because one, it's a very, very simple reaction. So it's in water. It takes less than 10 minutes to do, as well as it can be easily monitored through UV-vis spectroscopy. So we can see here, this peak at 400 nanometers corresponds to the nitrophenolate starting reactant. And as a reaction goes and product forms, this peak decreases, while this peak attributing to the 4-aminophenol increases. So by using the absorbance intensity here, we can actually plot the turnover frequency as well as the rate of the reaction with this. So first we kind of tried with the chitin nanocrystal. So from this, using gold, we can see that it gives relatively high turnover frequency numbers. However, if we would convert it and compare it, with bulk chitin, you can see that the bulk chitin actually provides lower turnover frequency numbers. So this is kind of correlating to the fact that we need the nanoscale nature of these nanocrystals for higher dispersity of gold and therefore more activity. Then we looked at using gold on chitosan nanocrystal. This is where we see almost 2 orders of magnitude difference in even lower gold loading. So in this case here, we can kind of really attribute the amine functionality in really kind of binding and creating a more highly dispersed gold system on our chitosan nanocrystal. And again, we compare this with bulk chitosan, where we can see that yes, it is still higher than bulk chitin, but the nanoscale chitosan just is so much more dominant than the bulk. We did some other control tests, such as using just colloidally stabilized gold nanoparticles, stabilized by carbonates. And we can see that it has higher turnover frequency numbers than the chitin nanocrystal. However, it's still smaller than the chitosan one that's supported on chitosan nanocrystals. We also did another control using the gold precursor, HAUCl4, and you can realize that it actually still gives catalytic activity. Now, this reaction can only happen with a metallic metal catalyst. So by using this test, this can actually further confirms that the sodium borohydride that's used to reduce the nitro into the amine, this is actually being this can actually also reduce the gold in situ. And this also means that this can actually reduce the gold 1 that is appearing on the chitosan nanocrystal itself. So the comparison with the literature, you can see we're comparing this first and foremost with cellulose nanocrystals as the catalyst support this is for all gold nanoparticles. And you can see that it blows everything out the water in terms of turnover frequency number. And we can see that even with graphene and cyclodextrin, carbon-based biopolymers, that actually blows everything out. So the unique chitosan nanocrystal amine functionality, as well as its nanocrystalline domain, really spurs it on to become really great catalyst support. So off this, we actually we tried to investigate another reaction, and so we picked the aldehyde amine alkyne coupling reaction for this, due to the fact that it's regarded in nature that it's not the gold 0 that actually catalyzes it, but it's in fact the gold 1,3 redox cycle that catalyzes it, such that oxidative addition, reductive elimination can occur. And so for our case, with gold 1 being the predominant species, this would be a really nice reaction to kind of further validate that. So we see that with just HAUCl4, so gold 3 oxidation state, we see that we get full conversion after 24 hours. While using gold nanoparticles with gold in the 0 state, we get relatively little yield. So once we use our gold on chitosan nanocrystal, you can see that with just 0.1 mole% loading, we're getting greater than 90% yield, which is really, really good in terms of using gold supported on a heterogeneous support. And if we just increase this to 0.5 mole% loading, you can see that this turns into full conversion. Now, if we decrease the time, it still provides a relatively high yield. And if we decrease the loading, of course, the yield decreases. However, if we go to relatively benign conditions of only 50 degrees Celsius as opposed to 70, you can see that we're still getting higher than 90% yield. And one interesting thing is that if we're using 100 degrees Celsius instead of 70, we actually see a decrease in yield. This may be due to the fact that we're actually decomposing the intermediates at such a high temperature. And so a summary of our work includes the first method to produce carboxylated chitosan nanocrystals using relatively mild conditions, which no one has done before, as well as using this material as a superior catalyst support for gold nanoparticles, outcompeting the literature for cellulose nanocrystals, as well as a lot of other different materials out there. As well as we attribute this to a unique dispersal gold 1 system that's owing to the chitosan amine present, as well as the carboxyl functionalities. So some future works in our lab include using palladium nanoparticles to immobilize it, to do more kind of applicable reactions, such as Suzuki cross-coupling, as well as Heck cross-coupling reactions, as well as finding a different way to make chitosan nanocrystals. So recently in our lab, we've kind of proven that aging is a very nice and effective way to deacetylate bulk chitin, and we just want to see if the chitin in the nanoscale can also be deacetylated using this way. So with that, I'd like to really thank my lab, Professor Audrey Moores, of course, as well as the NRC for all their help, as well as our sponsors. And I'd really like to take any questions during the discussion period. Thank you.